Good morning, everyone. We're just going to wait a minute or two for people to gather for this webinar, Improving Mechanical Reliability of Electronics. So good morning, everyone. This is Graham from KETIV. We're just going to wait a minute or two for people to gather before we get started on our webinar, Improving Mechanical Reliability of Electronics. So as people are starting to gather, I just wanted to set up a couple of ground rules. We're going to be going through a lot of material today on improving mechanical reliability of electronics. And I just wanted to make sure that please feel free to interrupt with questions at any time in the chat. And then I wanted to introduce Pedro as well. Who's going to answer questions as we go forward as well. And then with my turning off the video, I'm presuming, Bent, that the slides are full screen. Just wanted to double check.
Yes, you're full screen, Graham.
Okay, great. Yeah, so let's get started. So this morning, we're going to be talking about improving mechanical reliability of electronics. And two months ago, I introduced the electronic reliability webinar, looking at all 5 aspects here of different areas of electronic reliability: electrical, thermal, mechanical, comprehensive multiphysics, and reliability physics analysis. And then last month we covered thermal reliability in more detail. And this month we're going to be covering mechanical reliability and a little bit of the bottom one, reliability physics analysis. And we're going to cover kind of common mechanical failure modes, how Ansys can be used to analyze these in detail, and then how to use Ansys Sherlock to identify where you want to analyze the details for your electronic assemblies. So some common failure modes for electronics on the mechanical side tend to happen in the packaging and then in the solder contacts and the wire bonds, where you get stresses. And as you can see in some of these pictures, you get cracks happening from too high mechanical stresses, or in the bottom right, maybe a failure of the package where you then get some corrosion. And so these are the failure modes we'll be focusing on for today. And typically, there's a whole host of different failure protection schemes that you would use in the design stage to try and guard against these kinds of vibration or shock or fatigue or moisture errors. And they include such things as sealants, putting in an anti-vibration frame, having an enclosure, doing conformal coatings or potents or staking and or some sort of damping or shock mounts. And so the idea here is to find out before we've actually designed the part, before we actually created it, are these schemes adequate for the kinds of shocks or vibrations that the products will be seeing in their lifetime? And another component to using simulation on your designs is to look at whether your electronics are going to pass regulatory compliance requirements. In the vibration space, a number of these are listed, sort of IEEE 802, mil specs, IEC specs, et cetera. For fatigue and other drop tests and stuff, there are other different regulatory requirements potentially. And so the question is, can we pass these regulatory requirements before we actually get to passing the test officially? Can we do it in software? And that's the whole idea behind the value of you doing simulation, is reduce the cost and time to market by simulating designs prior to building them in the first place, and thereby reducing sharply the number of test and fix cycles that your normal design process might be using. So your typical process is design it, build it, test it. Do we have a fault? Okay, yes, and then fix it. And you go through a number of cycles of fixing it as you go through and find issues. If we can find those issues before we even build parts, we will save a huge amount of time. And that's the whole idea behind doing these sorts of simulations. So on mechanical reliability, we're going to be talking about solutions for fatigue, shock, vibration, and moisture ingress. And these are just some of the pictures of how these tests are conducted and what you might be examining in the software. And one of the key components to enabling accurate thermal and warpage and vibration simulations is to capture the amount of copper and the distribution of copper in each layer of the PCB board can really affect both the vibration transmission through the circuit board, but also the heat profiles as well. And so doing this sort of trace mapping of the copper and getting that accurate and meshing that accurately really enables us to dial in and have a very accurate analysis. So on the shock and vibration side, I wanted to go through some of the how Ansys does these sorts of analyses in more detail, and then we'll fold that back up into how we would start on the reliability side. So for doing this sort of structural analysis, when it comes to static static analyses, will this part break? Those are on the order of tens of seconds, hundreds of seconds a minute. But when we start looking at drop or impact tests, you might have a much shorter time horizon, 0.1 seconds. And then obviously, if you're doing ballistics or hypervelocity impact or something else, you might have even shorter time frames. And so Ansys has both implicit methods and explicit methods of solving these types of structural dynamics problems to really get at what's going on and will the part break and how will it react to your conditions in use. And for shock and vibration, typically you'd be using half-sine pulse excitations and evaluate the response spectrum or a transient, which can be explicit, like we were just showing in the last slide. On vibrations, Ansys can do random vibration analysis or harmonic vibration analysis to get a sense of what are the harmonic frequencies of the PCB board, and does that interact with the vibrations it's seeing, to really get a feel for what's going to happen and where things going to break down and affect your parts. And on the drop test side, there's a package called Ansys LS Dyna, which models these highly nonlinear events acting over a very short time duration. Anytime you're looking at phenomena that are less than a second, you would want to start looking at LS Dyna, and that simulates fracture, cutting, failure, buckling, impact, drop, lots of different short time frame scale events that you want to make sure your parts survive. And then on the moisture and hygroscopic effects, when you're looking at that, Ansys uses Fluent to analyze packages doing convection analysis, whether it's with temperature effects or whether there's other stresses, vibration, or coupled thermal vibration effects. You can do both. And then you can look at where you might have moisture trapped in a component and hydroscopic stresses developing, and then look at delamination and popcorn effects and so forth to determine whether your packages are moisture resistant. And then on the fatigue and fracture side, there are many different ways of looking at fatigue and fracture. We can look at it from a solder joint fatigue techniques, classic fatigue techniques, where you're looking at stress life and strain life approaches. You can compute the life, look at harmonic and random vibration fatigue. So all of these different ways of calculating fatigue, Ansys Mechanical has ways and methods of doing this. And similarly on the fracture mechanics, if you're looking at fracture, there are different stress intensity factors or J integrals, et cetera, and different ways of looking at crack growth and delamination. And you can examine a number of different methods using Ansys software. And as an example, for solder joint fatigue in particular, which is very relevant to electronics, typically the Darvaux approach is used at a more general level. And then if you need to do a more detailed analysis, there's a detailed way to do the Engelmeyer analysis to look at solder joint fatigue and analyze solder joints. As an example, the Darvaux method simulates at least 3 thermal cycles and calculates the accumulation of volume averaged nonlinear plastic work to look at solder balls and areas where they're potentially cracking. And then the Engelmeyer approach is taken at a much more detailed level, looking at fatigue ductility coefficients and exponents and so forth. There's a huge amount of both papers and additional help we can give you if you're wanting to jump into this arena. But what's key to all of this, looking at it from a electronics reliability perspective and my PCB boards, is how do we get to looking at sort of a global, here I have a PCB board, and now I'm trying to determine, well, how do I look at a particular solder ball? And is that solder ball the one I want to look at, or is another one? Or do I look at multiple ones, et cetera? And so what Ansys allows you to do is to look at the stress strain field, whether that's thermal or whether that's mechanical, of the entire circuit board to determine where on the board you would want to focus in on and do a submodel of the actual solder bump. So for this ball grid array that we're seeing here, you can tell that on the edges and the corners in particular, you might have the highest stress areas, and we're going to focus on those high stress areas first so that we know if that area survives the vibration or the stress that we're putting it under. The rest of the model, the rest of the ball grid array will probably be good. And so that's the approach that's taken here, is to do these submodels in areas of very high stress to verify and validate that the entire part will survive. And on the fatigue side, for harmonic and random vibration analyses, this is done by looking at a spectral distribution analysis, and there are different statistical methods of looking at that, whether it's narrowband, Steinberg, or Wersching. Again, there's more details here that we can go into maybe in another session or so, when you're jumping into looking at harmonic and random vibration and fatigue. So having gone through some of the specifics of how Ansys approaches looking at fatigue and vibrations at a more detailed level, how do we now integrate that into our reliability analysis? So how do we go from a detailed mechanical analysis to just estimating the mean time between failure for an entire assembly? And then how do we narrow down to one particular issue or an area of a board as a focal point? And so I wanted to introduce here something called Sherlock, which is an automated design analysis tool that examines and does this sort of mean time between failure calculation for electronic assemblies. And what it does is it starts out with simply the board components and board layout, and then immediately starts predicting what the potential lifetime for each individual component would be. And that allows you to focus on particular areas of the board or particular components. And then, as we were mentioning before, looking at the high stress areas and dial in and make sure that the board will take all of the different stresses that you're putting on it. So Sherlock has been developed and used for a number of years. And what Ansys has found is that organizations that use Sherlock within these sort of 4 different stages get the best return on investment. And those stages are first initial part selection or BOM creation. So when you're first creating the product and doing those initial selections, once you have that, if you start using Sherlock, that'll start narrowing in on what you need to focus on. Similarly, doing a preliminary design review or initial part placement area, that 2 parentheses area. And then on your critical design reviews, your finalization of your bill of materials and layouts, those are appropriate points to use Sherlock. And then once the board and assembly is in manufacturing process review or doing design for manufacture, that's again a last stage that Sherlock is very useful. Those are the areas where you can sort of affect the design. And if you find an issue, it's much easier to correct it within software than it is when you have started building hardware. And then more specifically, if there are particular areas of the design that are at issue, laminates, coatings or pottings, halt testing, some test plan development, those are also opportunities to use Sherlock. But it's a less global view. It's more kind of dialing in a particular part. So as I mentioned before, Sherlock calculates the mean time between failure for each individual component on the board. So you have a bill of materials on the board. It'll calculate what a mean time between failure is for each of those components. And it does that in a variety of ways. So it has a huge database of your typical capacitors and IC chips and so forth, resistors, typical components that are on a board. It's got a very detailed database of FR4 and copper and all the different board components that you might encounter, and then uses that database to examine for typical stresses that you define. It'll then do a very brief analysis of vibration fatigue and what kind of lifetime am I going to get from vibration fatigue, or thermal cycling soldering fatigue, or part through hole thermal cycling fatigue. And so and then all of that will get combined to get you an overall estimated lifetime for your parts. And so when you first start designing, you might have this being your lifetimes being very short. And then as you change the design to improve things, you can monitor that as you go through the different design stages in Sherlock, going from your initial design to your more detailed design to a finalized design, and constantly improving the lifetime of the product as a whole, and being able to examine all the sub areas as well. And that again guides you into, oh, well, maybe I need to do a specific analysis of this ball grid array because that chip's going to be at risk relative to some of the stresses it's seeing. And as you can see on the left side here, a little bit fainter, but there are 15 or 20 roughly different kinds of analyses that you can conduct looking at these sub-analyses. So that's shock, fatigue, natural frequency vibrations, random vibrations, solder fatigue, thermal derating, thermal mechanical analysis, etc. So there's a number of different relatively quick analyses that are done to enable you to sort of focus in on what do you need to look at to get this particular board and component to be reliable. And just as an example, in terms of how Sherlock is calculating these mean time between life curves, this is one example for solder fatigue. So the FEA simulation captures the peak strains of the component, and Sherlock uses a modified Steinberg equation with solder fatigue and strain versus cycles to failure, the SN curves, to calculate the characteristic lifetime. It then assumes a Weibull slope, makes some assumptions to get the beta, and that allows you to plot a life curve for each component. And then you have to go back and look at those assumptions sometimes and maybe dial in some. And then once you have the lifetimes for each component, it combines it for all the different components to get the entire board's lifetime as well. And as I said before, you have a number of different kinds of analysis you can do in terms of vibration, fatigue, et cetera, to again get the entire lifetime. So this is an example for the shock and vibration area. And you can see how this particular sample board has a 3D model, a estimated shock profile in terms of what kind of shock it might be undergoing in its lifetime, looking at the displacement in terms of how the board might bend under those shocks, and then estimates that the J1 and U10 and U9, those three components, looks like the lifetime might be is in red and is not going to last for what your specification is, and that most of the board is good. And this allows you to focus in on those three parts in terms of what kind of stresses are they seeing. Maybe there's some mitigation strategies that you might try in terms of potting or changing the mounting, and there's a bunch of different things you can try to improve things. But this allows you to sort of focus in on what needs attention relative to lifetime, relative to shock and vibration. And similarly, we covered it last month on the thermal side. Thermal cycling, of course, is a big lifetime driver or lifetime driving force for reliability on the electronic side. So thermal cycling is an issue, and similarly, thermal cycle analysis, whether it's solder joint fatigue or PTH fatigue, and thermal effects are also covered in Sherlock as well. This is just a very brief glimpse of sort of the interior of Sherlock in terms of the what's known as the product flow. And I'll present the next few slides just a brief analysis of this kind of flow, so you can get a flavor for it as an introduction. But essentially, you sort of start with up in the upper left here, your life cycle conditions and the electronic design files. Goes to get you an initial Sherlock design analysis, and then you start identifying where do I need to focus efforts in terms of my heat sinks or my geometry or my loads or conditions, and that leads you to doing a solid model analysis within Ansys mechanical, and there's a script that allows you to sort of automatically create those analyses and then feed them back and forth to and from Sherlock. And then you'll get out of that strain, displacement, temperatures, stress, etc. And those results will get fed back to Sherlock, and that will then improve Sherlock's reliability prediction. So you start with this, and you maybe do a few cycles here in the simulation side rather than doing it with live parts in the lab, which takes a lot longer. And so you can execute this cycle much faster and really improve your time to market and getting high reliability validated and proven before you can build the geometry. So on the life cycle conditions side, you start with trying to determine, well, what kind of vibrations is my part going to be seeing? Is it just the shaking of an automotive engine where I have a PCB in the engine, or is it something more gentle where it maybe is just in the back of a truck doing vibration for shipping? There's a number of different, potential types of shock or vibration that you could experience. And then within the program, you'll have descriptions of drop-down menus. This is very simple to sort of grab your typical conditions you might experience. And then of course you can modify it to whatever, if you know more about some of these shock events, you can modify it to your actual conditions, make it harsher, make it easier, change the pulse shapes, etc. So this is where you sort of start with what are my life cycle conditions, what kind of vibrations or shocks am I going to be withstanding. Similarly, on harmonic vibrations, there's different ways to look at harmonic vibrations in terms of duration, number of cycles, and sweep rate, etc. All of this is you have sort of your default values within the program, and then the ability to modify it as well. And similarly for thermal events, you might know it's, going down to temperature and going up, or it has daily cycles, or it has high engine temperature cycles, whatever. That there's obviously very different thermal conditions that any particular part might experience. And you start the analysis by defining those conditions here. And then the next step in the process is simply just to import all of the electronic design files. These are typically your Gerber files, ODB++, that define the traces, where all the parts are, what the parts are, the bill of materials. This is after you've done your initial layout. And with that, you can then start doing reliability analysis and looking at the stress and strains and how these might perform on the reliability side. And then on the pre-processing side, once you've started focusing in on, I have this particular ball grid array has really got an issue. Now I need to focus in on the solder balls for that ball grid array. And then you can start building that analysis within Ansys Mechanical and sending that analysis to Ansys Mechanical. So this is one example here of a modal analysis looking at vibrations, where we can see that when this board was vibrated, the highest level of strain and stress is in the middle of the board. So maybe we want to take these ball grid arrays and move them away from that point. Maybe we need to do something else to protect those areas. And it's these sorts of pictures that really enable you to focus in on which areas of the board do you need to look at next. And then, as I said before, those analyses of stress and strain then get fed back to Sherlock to improve the estimates, the sub-estimates for different kinds of thermal fatigue, vibration fatigue, et cetera, to look at your entire MBTF failure rate for the entire board. And go through that cycle of looking at where do I need to improve, and then improving it and dialing in. And so this is just one example on mechanical vibration. You might look at changing the loading, changing how it's mounted, changing what the direction of the PCB is, and then seeing what the response is relative to improving lifetime. And doing this sort of simulation allows you to really dial in and get to improved lifetime and or validation that you will hit your regulatory targets in terms of compliance as well. So while Sherlock does not tell you what to do in terms of what are mitigation strategies, it does allow you to test them. So we can look at if we change pad size or switch the package or change the laminate. There's hundreds or tens and hundreds of different things you can do relative to improving mechanical shock and reliability, but you can now test them and see, does it really make a difference or not? And dial in and get down to hitting your targets in terms of reliability and also, you know, avoiding recalls, which can be very expensive, etc. So in conclusion, I just wanted to say, you know, kind of introduce Sherlock as providing a framework for doing these sorts of mean time between failure calculations for electronic assemblies, and that it's supported by detailed Ansys mechanical analyses where you dial into where are the highest stress points in the board, where are the highest vibrations happening, can my ball grid array or my solder wire bond actually withstand those stresses, and then test different different methods of protection against them, and verify and validate the design. So I guess I'm wondering if anybody has any questions relative to this. So Bent, I know it looked like you were trying to had some full screen issues. We will be putting this out on the web again, so that you'll be able to go back and look at it again if that was an issue. As a video, we are recording this. But I guess I just wanted to see if anybody had any other questions on Sherlock or mechanical, how they interact. We definitely kind of did a whirlwind tour just of the capabilities. There's definitely more to dive into in terms of specifics, how to conduct the analyses. But we just want to be sure you know we're here for helping with that sort of thing, with support at KETIV.com, as well as just contacting me or marketing. Given that there are no other questions, I just wanted to say as well that there's an upcoming session next month, the second Tuesday of the month. Snigdha Sarkar is going to be presenting a webinar on high quality data visualization using Ansys Insight for CFD simulation. Insight allows you to gather and visualize data in terms of looking at flows and looking at your analyses in different ways. So that'll be really interesting in terms of CFD. And just have you mark those on your calendar as well for those interested. With that, I think we will conclude. So thank you everyone for your participation. I hope this has been helpful. I think at this point, this will be the last of our electronic reliability series for now. I will probably cover electrical and multiphysics, which are the two areas we did not cover yet, probably sometime in the fall, but I wanted to make sure the CFD folks got some of their chances to be on stage in terms of the AVAs. With that, we will conclude. Thank you so much for participating.
Thank you, Graham. Excellent presentation.